welcome to CS155. Sorry for the technical difficulties. Apparently there's two different projection systems in this room now. First time doing that for me. This projector seems to be a little bit muted in the color, so I apologize for that. I'll try to figure out how to use the new TV system for the next lecture if possible. But okay, welcome to CS155, cross-listed with CMS, CNS, and EE. This is machine learning and data mining. Raise of hands, who here are undergrads? And who here are graduate students? Okay, so about 50-50, great. So today we'll just be talking about some of the basics of machine learning, but first we'll talk a little bit about administrivia. So course info. Tuesdays and Thursdays, 2:30 p.m. to 4 p.m. So you all know that because you're here right now at the Beckman Institute Auditorium, which is this room. We have recitations as needed. They will be on Thursdays in the evenings. The location will be confirmed soon, and I'll send out the information as soon as that location is confirmed. And the recitations are basically a little bit deeper dive into topics that maybe some of you may not have as much experience with. So for example, if you're a PhD student in, let's say, biology, and you're not as experienced using Python as someone who has been studying computer science for several years, we have a recitation this Thursday on Introduction to Python. The recitations usually last about 45 to 60 minutes. Of course, they can go longer if people have a lot of questions. The staff, my name is Yi-Sung Yu. I'm the instructor of this course. We have a great team of TAs for this class, 14 in all. And they'll be the ones who will be managing the homeworks, any questions or hopefully not too many complaints about the assignments, holding office hours for the assignments, and that aspect of the course in general. And Matt Levine on the top left is the head TA. Okay, the course breakdown. Basically, there's 10 things. Each one is worth 10% of the grade. 6 homeworks, in total worth 60%. And that is a typo. I'll fix that. It's due Wednesday night on Gradescope. And 3 mini projects, each worth, in total worth 30% of the final grade. And a final exam worth 10% of the final grade. Some of you may have heard rumors about the final being a little bit different last year compared to previous years. For those of you who have heard such rumors, please be assured that whatever happened last year on the final will not happen again. And so it'll be in the same format as it was 2 years ago. Oh yeah, by the way, one more thing. Many of you are also taking this class concurrently with CS144 and CS139. For those of you who are, just please be aware of the exact due dates of when the homeworks are due, because especially with CS144, we have a similar cadence in terms of homework assignments and mini projects. Regarding homework 1, so this class is caters to a very broad set of students. Some have with various backgrounds and different levels of expertise in different areas. And so for undergrads, my expectation is that you have taken CS156. That's my primary expectation. And so homework 1 is sort of which will be released tomorrow, will be a checkpoint for you. If you've taken CS156 and did well in it, homework 1 should be pretty straightforward. If you did not take CS156, it might take a bit longer. If you are able to get through homework 1, you will, for the most part, have mostly caught up with the class. Of course, because this class does cater to such a broad audience, if you find yourself struggling a little bit with homework 1, maybe we can have a conversation, think about the prerequisites, maybe consider taking some more of the prerequisites, which are all soft prerequisites, except for CS156, and then maybe taking the class in a future time. But this is just so that you can help calibrate yourself. For PhD students, go for it. Okay, there's a late submission policy, up to 48 free hours in increments of 1 hour each. So if you submit a homework, let's say it's due next Wednesday at 9 p.m. And you submit it at 9:15 p.m., that you've used up 1 hour of late homework availability credits. And you should specify the number of late hours used when submitting. We will also keep track of that on Gradescope, and we keep account of that. Course etiquette. I welcome questions during lecture. I think it's a great way to keep the course interactive. If you have questions, it probably means several other people, either here or watching the lectures online, will have similar questions, and I'm happy to answer them. If it's too much of a disruption to the flow of the lecture, I may defer it in the interest of time, but by and large, I welcome questions during lecture. If you arrive late, if you need to leave early, I totally get it. Just please do so quietly. We have an updated collaboration policy. So the CS department, we created a new collaboration policy rubric last year. And it's been slightly tweaked this year compared to last year. And CS155 has adopted this collaboration policy rubric. You can find it on the course website. The basic idea is for homeworks, you can talk to each other. For mini projects, you work in groups. For the homeworks, if you are collaborating, that's totally fine. But in terms of copying answers from each other, that's not allowed. Observe the 50-foot rule. And for mini projects, you work in a team anyways. And for the final exam, no collaboration whatsoever. That's the gist of it. Okay, course website. You can find it on my website. My website is pretty easy to find, www.yisongyu.com. It's easy to navigate. You can find the course. Has up-to-date office hours, lecture notes, additional reading, homeworks, and everything else you need for the class. There are two main ways in which you interact with the TAs in the class. They are Gradescope and Piazza, outside of office hours, of course. Of course, there's FaceTime during office hours, but in terms of virtual interactions, there are two ways, Gradescope and Piazza. Gradescope is for managing assignments. We'll also post solutions and grades on there. And Piazza is for course announcements and Q&A forums. So please use the Q&A forum if you have questions about homeworks or anything about the class. The TAs are going to be very active on the forums. We'll also have all the lecture videos available online as well. Any questions about administrative stuff? Okay, so let's get on with the class. So machine learning and data mining. What is machine learning and data mining? So it's the process of converting data and experience into knowledge. So data are things that we're all now very experienced with. Everything you think of, has a data element to it these days. Knowledge is a computer model, and the process is an algorithm. So that's the nuts and bolts of what machine learning and data mining are. This class will touch on both aspects of machine learning and data mining. Machine learning, and to a large extent, they're more or less using the same set of tools. And so in terms of the nuts and bolts, there's a huge overlap. You'll be learning sort of all of it in terms of the basics. But when we think about sort of what these methods are used in service of in terms of higher order activities, machine learning focuses more on the algorithms, so typically a bit more mathematically rigorous. Data mining focuses more on sort of the knowledge you can extract from this data set. These days, data mining is also more popularly known as data science. So perhaps we should update the name of the class, but that's a paperwork nightmare, so I choose not to. But you can think of data mining as data science. Typically uses machine learning algorithms, and the knowledge that it's extracted should be, in some sense, human understandable. But again, in terms of the nuts and bolts and the tools used, very large overlap. Okay, so here's the course outline. We're going to spend 5 weeks on supervised learning. which will be the bulk of what you get out of this class in terms of practical stuff. Supervised learning is the most popular paradigm used in industry today, and also one of the most popular and most successful paradigms used in various domains across the sciences as well. We'll also spend about 2 weeks on unsupervised learning, which is also quite popular in many scientific domains where you don't necessarily have a supervised label. And we'll conclude with 2 weeks on probabilistic modeling, where we think about probabilities and generative models and how to reason about uncertainty. So let's start with supervised learning. So in a nutshell, supervised learning is about finding a function, also known as a mapping or a predictor or a hypothesis, that maps from some input space X to an output space Y. And we often use 2 letters to denote this mapping. One is F and the other one is H. I'll use them fairly interchangeably in this class, although sometimes one will have a specific meaning. But you can think of both F and H as you see these things in the literature, whether it's on Wikipedia or some research paper you're reading. They often refer to the predictor or the hypothesis or the mapping as F or H. And the goal is to learn such a predictor such that prediction error is low on a pre-collected training set, where we have these labels Y. So examples include fake news detection, where if X is a piece of news and Y is a label, is this fake news, yes or no? Then given such a pre-collected training set of XY pairs, the goal is to find an F or an H that can accurately predict the corresponding Y when given an input X. Another example is if X was some set of DNA sequences and Y was an indicator of whether or not this DNA sequence encoded a specific function or is of a specific category, yes or no, then given this a pre-collected training set of such XY pairs, find a F that has a low error on the pre-collected training set when it tries to map X to Y. The final example is if X is a molecular compound and we want to predict, let's say, a real value property rather than a categorical property, let's say the thermal stability of this particular compound, then again, we want to find an F that has low error in terms of this mapping on a pre-collected data set of XY pairs. So that's supervised learning in a nutshell. And so you get this data set, X, the raw data, if you will. You have some target signal Y that you have access to. In this case, let's say the X is movies on Amazon, and the Y is the average rating of these movies on Amazon. And so now, given some attributes of a movie, we want to be able to predict the average rating. That's the learning problem, the supervised learning problem. We feed the XY pairs into a machine, and we run a machine learning algorithm and it spits out an F such that for this set of XY pairs, the F basically hopefully is very accurate and it predicts the more or less correct Y for any X in the training set. That's the hope. And there are many ways to do these. There are many methods. Deep learning or artificial neural nets are very popular these days. More conventional methods or classical methods such as logistic regression remain very popular, and there are other methods as well. And we will cover each and every one of these methods throughout this class. And you could think of these as what's called a function class or a hypothesis class of functions or predictors. That's just the terminology that we use in machine learning, or the space of functions that we're learning over. Okay, so as an aside, so for unsupervised learning, which we'll cover a little bit about halfway through this class, there is no supervised target. We only have the raw data. And so the goal, rather than to find a prediction target that we can learn to map to accurately, the goal is a little bit different. It's some notion of finding a low-dimensional summary or reconstruction of the data set, to find a low-dimensional pattern that explains the variability of the data. And I'll get to many examples later on in this course. Any questions so far? Okay, so let's dive into an example, one of my favorite examples, spam filtering. So the goal is to write a program to filter spam. This is a very important problem. If you ever looked at the spam folder of your email, you'll realize why this is a very important problem. It's also a very hard problem. So to sort of think about why it's hard, let's go through a few examples in a thought experiment. So imagine we had this email, and that's the subject of the email. Raise of hands, how many of you think it's spam? Raise of hands, how many think it's not spam? Okay, good. So we're all in agreement that this email is spam. I also think it's spam. Next email. Raise your hand if you think this email is spam. I don't think any of you will pass this class. Raise your hand if you think it's not spam. Good. Okay, I also think it's not spam. Final example. Raise your hand if you think this email is spam. And raise your hand if you think it's not spam. I fear for your bank account. I think it's spam. Okay. Now let's write a program to actually filter these emails. If you just took CS1 and you learn how to program in Python, your first instinct might be to write something like this, right? So my first instinct, as a freshman who just took CS1, might be to write something like this. There are a lot of problems with this as a spam filtering program. One is it is extremely brittle. If things don't match perfectly in the if-then-else statements, then it'll get through the spam filter. If I come up with a new case of something that should be filtered, I need to add another line to the if-then-else statement. And so these are just two examples of why this process is very brittle and hard to do manually. So why is spam filtering hard? Just to summarize, it's somehow easy for a human to recognize, but it's hard for humans to write down a prescriptive algorithm. Right? So if you were to do that, it would be a lot of if-then-else statements with some backtracking, with partial matching of words and all that stuff. So it's really hard to write down an algorithm, but in some sense, it's easy to recognize. There's some notion of a label that we can provide quite easily, much more easily than we can sort of write down an algorithm for or program for explicitly. And so these are one class of problems, one of the biggest class of problems where machine learning has a lot of leverage and has a lot of value. And so it's not the only class of problems, but we'll focus on it for this lecture. So let's think about how to use machine learning to solve this problem. So again, we're going to do supervised learning. So we'll have a training set of emails and a label of spam or not spam. We'll assume that it's relatively easy for humans to provide this label, certainly much easier than actually writing the program in this particular example. And so this is our supervised labels training set. So the emails are the raw data, the X, and the spam or not spam labels are the binary labels or the supervised labels Y. Step one, we need to build a representation of the raw data. Step two, we run a learning algorithm on this supervised training set with this representation of the data. And from that comes a classification model that can classify, given this representation of the raw data, whether or not this email is spam or not spam. Okay, so there are many ways to build a representation of the raw data. We'll go through several in this class, but for the purposes of keeping it simple in this lecture, lecture one, let's just use what's called a bag of words representation. So a bag of words representation is constructed as follows. It gets more complicated, but this is sort of one of the simplest versions, arguably the simplest version of a bag of words representation, which is arguably the simplest representation of text. And so let's assume that we have a vocabulary of words that we care about. For the sake of this example, let's assume that vocabulary is size 6. So a bag of words representation is a vector of values, in this case binary values, where if the word corresponding to the entry of that vector appears in this email, we'll put a value of 1 in that entry, and otherwise put a value of 0. So appearance or not appearing in the email. So obviously it can get much more complicated. You can count, you can do other things, but let's just stick with this as the example. This is also known as a feature vector in machine learning terminology. So you'll hear that come up a lot if you listen to machine learning talks or read machine learning papers. A feature vector. This is a feature vector. This is a featureization of the email. In practice, of course, we can have tens of thousands or millions of words in our vocabulary. We may even have billions of words in our vocabulary. So for example, if you want to build a bag of words representation on Twitter, people abbreviate, people misspell, people have hashtags, people do all sorts of stuff on Twitter that are results in non-canonical words. And if you want to actually capture all of that, if you did want to do that, that would lead to a bag of words representation that could be, a billion in length. Next, we need to choose a model class. So, for the purposes of keeping it simple to go through a concrete example in lecture 1, let's use linear models. So let X denote the bag of words representation or the bag of words feature vector representation of an email. So for example, for any given email, we basically write it as, let's see, where's my mouse? Right here. We basically write it as this X, which is a vector of binary values of length 6 in our example. A linear classifier basically takes all the entries of this vector and does a weighted sum of it and then checks if that sum is greater than the threshold. For those of you familiar with linear algebra, this is also known as a dot product. So we have this W. This is a parameter of our linear classifier. And this is called a dot product. And if you're not as familiar with linear algebra, we'll have a recitation on linear algebra later in this course in like a week or two. What that basically means is it's a for loop over the entries of this vector where we do this weighted sum. And we check if this weighted sum is greater than some threshold B. That's also a parameter of our linear model class. And if it's greater than this threshold B, then we predict yes, it's spam. If it's less than this threshold B, in which case the value is inside the sign function is negative, then we predict no, it's not spam. Any questions?
In this paradigm, do we assume sign 0 is 0?
In this paradigm, we so the question is, do we assume sign of 0 is 0? In this paradigm, we typically don't assume that the value inside the sign function is exactly 0 after you've learned a model. For technical reasons, yes, we assume sign of 0 is 0. In practice, that basically doesn't happen. No. It's always, either greater than or less than 0 after the model's learned. Okay, so this is an example. So here's our supervised training set, our bag of words representation. Our goal is to learn the W and the B from this supervised training set such that the output of this sign function is positive on the emails that are labeled spam and negative on the emails that are labeled not spam. That's the basic idea. And that's what a machine learning algorithm will do when given the supervised training set and a specification of a model class, in this case, linear models. And on the top right, for this very simple example, here's the instantiation of W and B that will give you perfect classification, at least on the first 6 examples in the training set. And of course, if you're curious, you can work out the math and the arithmetic yourself offline. Okay, so you've actually learned a lot about machine learning already. So linear models are actually even in the age of deep learning, linear models remain a workhorse of machine learning. They are used in industry. I think they are still the most popular models used in industry right now, in terms of everyday usage. And if you just have a feature representation, collect a supervised training set, train a linear model, and then if the model checks out, you can deploy it and use it in production. So let's talk about some other issues. Why might we expect this process to work at all? And the reason why we expect this process to work, or I think the best reason, is that there are repeated patterns in the data. And ideally, these patterns are captured in your feature representation of the raw data. So for example, the words Nigerian prince is typically indicative of spam. And so observing those words and assuming those words are captured in your representation, then you will learn a pattern from a large training set that these words are indicative of spam. You put a high weight on those words. Your learning algorithm will learn to put a high weight on those words. So that's the idea. And so there are two basic supervised learning paradigms. The first one is classification, as we've just saw, where in the simplest case, it's binary classification, although we can go into multi-class as well. And in binary classification, you basically do this weighted, for a linear model, you do a weighted sum of the attributes of the feature vectors. And then you see if it's above or below a threshold. If it's above, then you predict the positive class. If it's below, you predict the negative class. The other type of supervised learning is called regression, where the goal is to predict a real value rather than a category. And in which case, the simplest thing to do is just not have the sign. So all we're doing is we're just taking away, we're taking away the sign in classification. We just don't have that. We're just literally just returning the raw score of the linear model. And that we use that for regression. Question, yes?
Yeah, sorry, but going back to the last thing, with using this approach, like, for instance, say the word Nigerian since appears separately is, versus them appearing together, if they're appearing together.
Okay. Yeah. So the question is, in this specific example, Nigerian prince is a compound word. And the bag of words representations basically destroys any notion of compound words. If Nigerian prince appears, it flags the Nigerian feature value. If prince appears, it flags the prince feature value. And if both appear, they flag both. But how do you know if they're appearing together in the text? And the way you get around that is to use more expressive feature representations that include compound words in your vocabulary. We will talk about more expressive feature representations later on in this class. But that's a great question. So that's an indication of a weakness of the expressiveness of this particular feature representation for this problem. Okay, so back to classification and regression. So they're actually highly related. As you can see, the form of the function classes are very similar. And in fact, you can train a model to do regression. So I could treat these labels, these spam or not spam labels, just as +1 or -1, positive or negative. And I could just train a regressor to try to predict a real value number and then just take the sign on it afterwards. It may not work as well as training it for classification, but in some sense, it can work pretty well. And we'll talk more about the relationship between regression and classification later on. Okay. So if I took away if I go back to this example where I constructed this W and B model that had perfect classification accuracy on the first 6 examples, and I take away the sign function, I don't use the sign function, here are the actual raw scores before you take the sign. Any questions? Yes?
So this filter actually wouldn't be a good model for regression because if you're doing supervised learning, you don't know how much to give to each of the spam or not spam in the beginning because you don't have to W in the first place, right? Or
you learn so you learn W and B as part of the learning algorithm over the supervised training set. So you're given the supervised training set, you're given this representation, you're given the fact that you're using a linear model class, which basically corresponds to a W and a B, and the learning algorithm learns a W and a B. Here I handpick the W and the B, but the learning algorithm will learn it automatically.
But why put in the email, but then for Y,
It's, oh yeah, it's +1 or -1. So spam is +1, not spam is -1. In this simple example. Okay, so some formal definition. So this notation is fairly common in many machine learning papers and textbooks, but it varies a little bit. We have a training set, I'll call it capital S. And it's a set of XY pairs where capital N is the size of your training set. And X is assumed to live in a d-dimensional, is assumed to be a d-dimensional feature vector. And Y in this case is binary. This notation is fairly common, although you'll see some variations of it. We have a model class, also known as a hypothesis class, in this case linear models, that are and the parameterizations of this linear model class is a W vector and a B scalar. And the goal is to find the parameters of this function class that predicts well on this training set. And so the remaining thing that we need to talk about is how to quantify well. And that's where we come to loss functions. So that's the next step in the basic supervised learning recipe, which is the choice of a loss function. A loss function specifies, one second, a loss function specifies the degree of mismatch between the ground truth or the true supervised label, I'll call it the first argument A, and the prediction of your model, I'll call it the second argument B. Question?
Is there any loss of generality of assuming that you can represent any input as some number of real numbers?
The question is there any loss of generality assuming you can represent any input as a vector of real numbers? Yes, there is loss of generality. So for example, if I can just give you an example. I can represent any function using as a linear function if the basis of that function, if the feature values are the Taylor expansion of that function or something related to the Taylor expansion. For functions with bounded number of derivatives, then it's finite. For functions that have an infinite number of derivatives, then you lose representation power for any finite length feature vector. Just as one example. There are others, of course, but. Okay, so this particular example is squared loss, where we characterize the mismatch between the first argument, the true supervised label, and the second argument, the predictor of our model, A and B, as quadratically increasing as they differ in disagreement, as they increase in disagreement. And this is a choice you'll have to make to be able to quantify how poorly a misprediction is. And then given the choice of a loss function, we now have what's called the learning objective or the learning problem, where we want to find the W and the B, the parameterizations of our linear function class that minimizes the sum or the expected value, if you divide by n, of the loss over our training set, where the first argument is the true supervised label, and the second argument is the prediction of our function class given that W and B on input X sub I. And the learning algorithm is then going to try to find the minimizer of this optimization problem. Yes?
So the loss function B and all different, where B in the loss function is the entire Wx minus 1.
B in the loss function is the output of F.
Right. So
Yeah. Yep, that's right. Oh, I see. Because I used B here in two different contexts. Okay, so this B has nothing to do with this B. Okay, sorry for that. Okay, so there are many different choices of loss functions that we can use. So for example, for classification, the loss function that people prefer, if they can use, is 0-1 loss, where it's basically do A and B agree on their sign, basically? Yes or no? Depending on what the input format of A and B are. Do they agree on their sign? If so, the loss is 0. If they disagree on their sign, the loss is 1. So in the special case where the sign is 0, then you still incur a loss of 1 because they disagree on their sign, and the ground truth is either positive or negative. We've seen squared loss. And so these are sort of the two canonical examples. That the 0-1 loss is used for classification, or is preferred for classification, and squared loss is preferred for regression, typically. And we can plot these out, right? So if the target label was, so if this is assuming x was one-dimensional, so x is just a one-dimensional feature that a scalar. So it's just a scalar feature value that takes attribute value between -2 and +3, and the target. Backtrack slightly. Let's say I confused myself. Forget what I just said in the last sentence. This is the output of f. The x-axis is the output of f of x, which is a real scalar value. The target that we want to predict is 1. So the target is a positive label. If we were treating this as a classification problem, we would take the sign of this scalar value. So at 0, for negative, we will predict -1, and for positive, we will predict +1. For regression, we would just take the raw value of the linear regressor. And so here I'm just plotting a comparison of the geometry of squared loss versus 0-1 loss, where for squared loss, obviously you see this quadratic shape where as you deviate from the correct prediction of +1, the penalty for the misprediction increases superlinearly. For 0-1 loss, as soon as our predictor predicts a positive value, the loss is 0 because we take the sign. We compare the sign of the values. As soon as the function, the predictor, has a value that's negative, we incur a loss of 1. Because again, we're just comparing the sign of the prediction versus the sign of the label. So this is this is sort of a geometry of the problem. Notice also that scale doesn't matter. I can multiply everything by 10 or multiply everything by 0.1. It doesn't change the minimizer of this optimization problem. Only the shape differences change the minimizer of this optimization problem. Also note that if I were able to learn a W and a B that gets perfect regression error, so perfect squared error, it would also get perfect 0-1 loss. But the reverse is not true. If I get perfect 0-1 loss, it doesn't necessarily mean I get perfect squared error. Because I could be predicting, something over here or something over here. That's perfect 0-1 loss, but that's not perfect squared loss. Okay, so suppose I wanted to get perfect squared loss on the first 6 examples of my training set. In which case, I wanted the raw score of the linear model, not the sign of it, but the raw score to be exactly +1 or -1 on these 6 examples. Well, I handpicked this, but this is an instantiation of W and B that can achieve perfect squared loss on the first 6 examples, rounded to the second decimal place. Okay, now let's talk about learning algorithms. Right? So this is one of the homework assignments. Right. So I formulated mathematically what the machine learning problem is, at least in the case of supervised learning. We have a function class f parameterized by some parameters, let's say W&B. We have a training set of n examples with an input instance, with representation of the input and a label, and we've defined a loss function. And the goal is to find the parameterization of our function class that minimizes the loss on this training set. Right? So this is the mathematical formulation of the goal of machine learning, right? If we had something that can solve this optimization problem, then we've done our machine learning. In practice, solving this optimization problem requires some kind of optimization algorithm. And a lot of machine learning is about figuring out how to design and implement learning algorithms. A learning algorithm, at least in the case of these sort of fairly standard supervised learning setting, is basically how do you solve this type of flavor of optimization problem. The simplest thing you can do is called gradient descent. Arithmetic tool here has taken multivariable calculus. Okay, so it is the majority of the class. If this looks unfamiliar to you, recitation next Thursday will cover some of these topics. So the basic idea is we have some initial W and B, so initialization of parameters. And since we're trying to minimize this loss function, we want to compute given this current W and B, we compute the gradient with respect, we want to decrease this, we compute the gradient of this whole function with respect to W, and then we go in the opposite direction of the gradient, because we're trying to minimize this loss function. We'll do the same thing. So this is basically the foundation upon which most of machine learning is based off of in terms of learning algorithms. And so this happens in a sequence of steps, where little t here denotes the iteration of gradient descent. So we start with some W0, and then you iteratively update this recursive formula, where you increment t as the number of iterations goes tends upwards, and then at some point you converge to a W and B that has minimum loss, or you converge to something that where you can't get better. Right? And that is how gradient descent works. The number of iterations can vary. For simple problems, you might start converging after like 500 iterations, or maybe even 20, depending on the problem. For very hard problems, it may take millions of iterations. And I'm sure someone's going to ask, how do you know if you've converged? And that is not as philosophical of a problem, because that is very rigorously studied in the optimization literature. We won't be going into too much detail about that in this course, but we'll look at some empirical ways of estimating whether or not you converge or not. Any questions? Yes?
Are there problems of local minima?
Right, so we're not going to talk too much about convex versus non-convex optimization in this class. We'll deal with it a little bit in the second half of this class. In the first 2 or 3 weeks, everything's convex. So, for example, in the homework assignment, it's a convex optimization problem. There are no local minima. And in general, if there are local minima, most of the time, people in machine learning just close their eyes and hold their ears and pretend it doesn't exist. It's sad. Okay, so you look at here. Okay. So just a quick overview. So this may be useful for people who haven't seen this material before for their homework assignments. How do you compute this gradient? Right, you have this loss function. You want to compute the direction of steepest descent with respect to the parameter W. And the way you do that is first you apply linearity of, and I apologize, this is probably review for almost everyone in this class, but I want to make sure everyone knows all the details. First you use linearity of differentiation to move the gradient inside the sum, and then you apply the chain rule. So if the loss function was squared loss, which I believe it is in the homework, then you sort of write out this loss function, which is the square thing, which is the square difference between the first argument and the second argument. You apply chain rule, so now the gradient operator applies to this path because you want to take the derivative of W, and then you take the derivative, since it's a linear model, you take the derivative of W to state X, and this is the gradient for squared loss for the linear model class. Any questions on this? Okay, so more details about this. Okay, so now this is the optimization problem. We want to minimize some loss function with respect to the model parameters on our training set, right? But, okay, so squared loss, I computed the gradient, no big deal. It's a differentiable function. How do you actually compute the gradient for 0, 1 loss? Does anyone see any problems with doing gradient descent on 0, 1 loss? This loss?
I'll speak up at once. Yes.
There's like a jump. So
yes. So there's this continuity here, which is not differentiable. That is one problem. It's a very, very big problem. There's another problem. Yes.
Sure.
Yeah. You.
In the flat region, you don't know which direction to go.
Great. So the gradient is undefined or zero everywhere, right? So it's undefined at the points of discontinuity, and it's zero everywhere else. Right? Which means if you're here and you know you're making the wrong prediction, you don't know which way to like move your model parameters to go towards this way because it doesn't go down, right? The way you solve this, you want the loss function to go down, and the loss function is flat. For square loss, you're like, okay, well, if I go this way, the loss is going to go down, right? For 0, 1 loss, it's like, well, if this is my loss function, if I go this way or I go this way, I'm different. If my goal is to minimize loss function. So minimizing directly for 0, 1 loss within this framework is actually extremely, extremely challenging because the loss function is flat. It doesn't actually guide you towards a good prediction unless you're already in a good prediction. So in optimization, we sometimes say 0, 1 loss is intractable. Right? It's fine, it's everywhere, very good to optimize. And the solution that people do in machine learning is to optimize for some sort of surrogate loss function. Some loss function that is differentiable. And if we optimize well on that, the surrogate loss function, we have some confidence that it will also do well, on zero loss. For example, square loss, as we mentioned before, if you get perfect square loss, that implies perfect 0, 1 loss, right? And square loss is something that's easy to differentiate and optimize, right? So square loss is a surrogate loss function for 0, 1 loss. The broader sort of lesson here is that when people talk about training classification models, and they're solving this optimization problem, they are almost always solving a surrogate loss function that's actually a regression line. Right? That's the sort of high level. That's the high level sort of lesson. In this case, it's squared loss regression. For this particular case, you'll learn about logistic regression in this class. But that's sort of the high level lesson. And be smooth. So anything that's smooth is really some notion of regression. Okay, so just to recap, these are the two basic machine learning settings for supervised learning classification, where the goal is to predict a small number of discrete classes. In the simplest case, 2 discrete classes, so just the sign of the scores. Regression, which is the goal to predict a real value number, and the two are highly related, right? Oftentimes, when you train a model for classification, you're also implicitly training some sort of regression model because it's smooth and therefore differential.
So is minimization of 0, 1 loss, so is it actually an incomplete problem? It looks like Boolean satisfiability.
Yes, yes, I believe that I'm on camera, so but yes, I believe that it is, versions of it is incomplete. Although you shouldn't quote me on it because it's been a while, I don't remember exactly. But no, I mean, in practice, almost no one optimizes their reserve because of these problems. Yes?
Do you see a difference between a regression problem and a classification problem with infinite classes?
With infinite classes. Okay, so, I mean, there's countably infinite and uncountably infinite, for one, right? And so regression, if you're going to be super pedantic about it, is uncountably infinite. But I can predict all possible natural numbers, yet that's still not a regression model in the extreme case. To actually answer your question, actually I'm not sure like what you're getting at with your question. Is it sort of more of that philosophical question, or is it something more practical?
Just in practice, I'm wondering if there's...
I see. In practice, classification is really not that many classes. Right? Like even something like, if I'm a web company, I want to predict whether or not a website, like let's say I'm a web search company or Facebook, I want to predict want to categorize websites or links that people share into like, is it about politics, is it about shopping, whatever, there's at most like 1 million classes, right? So it's like some possibly very large, but in the grand scheme of things, very finite number of classes, right? So no one actually ever thinks about infinite classes for classification because 1 million, well, large, is small in the grand scheme of things. So in practice, this issue never comes up. Yes?
What if you wanted to give something like a score between 0 to 1 and it matters like really close, like which is better, right? Then it's like uncountably possible scores. Like if it matters that the amount of precision that you have, like one object can be better than another by a very small difference.
So the question is, what happens if the score difference matters? Yeah. If the score difference matters, then it becomes a regression problem. The question earlier was about what is the difference between regression and classification where you have an infinite number of classes. And from that sort of viewpoint of thinking about how to model problems, that issue never comes up in practice. If you're concerned about what happens if I really want to nail down the difference of how much better one thing than the other one, that's a regression problem. So that falls into the second category. And it does happen a lot of times. Yes?
So in practice, you have like finite amount of bits to encode numbers. So does it actually mean that you can just use classifier for every bit in order to basically to convert classification into regression?
Okay. Let me see if I can understand the intent behind asking this question. So, if I take your question at face value about whether I can, there's a finite number of bits and whether I can convert classification to regression, if I take your question at face value, that is one of the most inefficient ways to use machine learning I've ever heard of. Right? So in practice, no one would ever do that. As a more philosophical point, yes, you could do that, but the problem now becomes much higher dimensional. Like the number of parameters that you're learning, which is one for every bit, is much larger than what it is right here. And we'll talk about things like concepts like overfitting, actually, in just a few slides, where if you have too many parameters in your model, you need a lot more data to reliably learn those parameters in your model as you overfit. And that'll become clear in the next. And that's one of the reasons why no one ever does stuff like this in practice. And that'll become clear in the next few slides. Yes?
So I just wanted to say that I think in regression there's a notion of distance between your prediction and the ground truth, whereas in classification that's not necessary. And I think that's the fundamental difference between regression and classification.
Although I agree with you in terms of, it depends on how, okay, so the question or the comments that I'm doing recording is that in regression there's a notion of distance, whereas in classification it's either you get it right or you get it wrong. Well, that is true from that perspective. There's also a different perspective where that's not true. Right? There's a notion of stability in classification, right? Like if I make a prediction right here, I'm classifying it correctly. But maybe if you just add me a few more data points, or subtract a few data points, then my prediction, I'll learn a model that predicts something over here. Right? And so there's a notion of stability in your classification model. And that is very closely related to distance. So, you collected 1,000 examples, you make a bunch of predictions, and all the predictions seem to be closely to the boundary. Are you actually confident in the wild your model will do well? Right, so those are the questions you need to answer. Okay, so just to recap, supervised learning, training data, where you have X represented as a high-dimensional feature vector, D-dimensional, Y in the simplest case for classification, just plus 1 or minus 1 as the labels, and this is the data you're given. You have a model class and layer models. You have define a loss function, let's say squared loss. You minimize this using some optimization procedure, and you're done. Right? Congratulations. You can go off and profit. Right? One thing that we haven't discussed yet is how do you know that your model is any good? Right? How do you know whether or not your model is doing a good job? You minimize some loss function on your training set, and so you think your model is good, but how confident are you in it really? Right? And to sort of think about this question in a more sort of rounded setting, let's think about self-driving cars. So nowadays, self-driving cars are almost a reality. This was not the case 30 years ago when people first started thinking about self-driving cars. 30 years ago, people did something like this. They mounted a camera on some car. They used some image-based features. I won't go into details, but used some image-based features. And then they recorded the driver, sort of the angle of the steering wheel, how much the driver pressed the pedals, so on and so forth. They instrumented the car, and they recorded all of the, let's say, the steering wheel angles of the driver as the driver saw this image, right? And so those are called human demonstrations. That's your supervision, right? So the goal then, in the simplified setting, is given some image features of the road, F is going to predict the steering angles, right? And this F is parameterized by some, parameters W. Right? And so, what you do is you just drive around, collect this image as an X, collect the steering wheel as your Y, drive around for a few hours, you have a training set, that's train a model to predict steering angle as a response to imaging. Standard supervised learning setting. Okay, so in training time, you learn a super accurate model. It seems to always be able to predict the train steering angle really, really well. So they tried it, in the real world, and it crashed. Right? Why did that happen? After a while of debugging, the researchers realized that their model, W, learned to only care about staying between two green patches. Right? So it turned out that all their training data was collected from roads that had grass on either side, on both sides. And that turned out to be the most statistically salient pattern, right, in that training set. So the machine learning algorithm decided to just focus on that. You drive on the road with no green grass on both sides, and the car is just going to crash because it's unexpected behavior. Right? So even though you collected the training set, you minimize square loss, let's say, really well in this training set, you can still do horribly in the live test setting. Right? And the reason is because you overfit to a training set that was not actually representative of your true test case. Right? So just because you minimize square loss, or minimize whatever loss function you cared about on your training set, does not mean that when you actually train the model, it'll actually work well, because you need to make sure that your training set is representative of your test scenarios. And this is related to an issue called overfitting. So, a little bit more notation. So, in machine learning, we think about something called test error. What that means is there's some true distribution of x, y pairs. So, given this input instance, this is the correct prediction that you should make. And there's a distribution of that. Unknown to us machine learning people, right? So, x could be all possible emails, and y would be the labels, spam, that's kind of what this is. What we're given is a finite sample from this distribution. We've collected a finite sample from this distribution. That's our training data. And in machine learning, in supervised learning, we typically make the assumption that every XY pair is sampled independently from the true distribution. And so we're training F to classify Y given X on this training set. Test error is then defined as the error that your trained model makes, right, on the true distribution, right? So you minimize error on this empirical distribution. Test error is the error your model makes on this distribution, right? In the self-driving car sample in the previous slides, this wasn't even sampled independently from this. It was sampled in a very biased way from this. It was not represented at all. So minimizing this does not at all imply minimizing this. Yes, question.
You always know the true distribution.
The question is, do you always know what the true distribution is? And the answer is, you never know what the true distribution is. You only know that you have some mechanism to collect data from, some finite set of data. Overfitting is the case where the test error is much larger than the training error. So this is not like a super formal definition. Technically speaking, you're overfitting. Whenever this is greater than this, you are overfitting. But the regime of severe overfitting is when this number is much higher than this number. And that's what you should be concerned with. Because it means that your model has learned something about the idiosyncrasies of this data set It is not, in general, true of the test case, of all test cases. Yeah, so this is test error. So I'll call this test error loss with respect to this distribution, capital P, of some function f. Now, one of the things that people often do is they think, and this will become more useful in about a week when we talk about bagging and boosting, is that people often treat the learn classifier as a random variable, right? When they analyze these types of methods. What does that mean? Well, suppose our training set was something that we collected sort of randomly, right? If we could somehow repeat the training set collection process, we would have a different training set, right? So you could think of the training set as a random variable, right? And our classifier is trained, in this case, let's say in a deterministic way from given a training set. So therefore, our classifier is a random variable. The randomness comes from the randomness of our training set collection process. So this is a, let's say, deterministic process, but the collection of tests, since S is a random variable, as we collect data at random from the true distribution, then this F of S of S is a random variable. So then we talk about things like expected test error. Over the randomness of our training set collection, what is the expected test error of our model class? So now, because now every time I'm picking S, we can pick an F from our class of models. So this is known as the expected test error of the hypothesis class with respect to training sets of this size. And these are quantities that will get covered in numbers and stuff. So the last technical thing I think I'm going to talk about today is called bias variance. And this is very important when thinking about what type of model class to use, right? So one of the questions that may be in your heads right now would be something like, okay, so overfitting is a problem. How do I deal with overfitting? How do I think about overfitting in a way that so that it's not as big of a problem as it can be? And one way to sort of think about it in a more mathematical rigorous way is to think about the bias variance decomposition of your model class. So this is the expected error of your model class, the expected test error, of your model class. For squared error, this L is basically the square difference between the first argument and the second argument, right? And if you just rearrange a bunch of terms, just standard arithmetic, algebra, and using the distributable, associable, stuff like that, standard algebraic tricks, you could rewrite, if you essentially this is square, you could rewrite the expected loss of your function class as these two terms. Right? The first term is over the expectation of your training examples. What is the difference? What is the average square distance between the prediction of your model, learned model, versus the average prediction? So capital F sub x is the expected model, prediction of the expected model, the expected prediction of all the models you train. So what that means is if you were to draw a bunch of training sets of size, let's say 1,000, over and over and over again, and you train a model F using that training set, and then you average all the predictions together, capital F sub x is that score, right? And so this term is called the variance term. It's how for any individual training set and the model you train from this training set, what is the variance of that model from the average prediction? This term is called the bias term, which is what is the difference between the average prediction over all the models in a model class over the randomness of a training set relative to the ground truth label, the target label of this test example. So this is called the bias variance decomposition of the test error of the model class. What this means is that when you train a model on your model class using data sets of this size, and you expect to get this type of test error on it, mathematically, so we can characterize this, that either the test error is what's contributing to test error is either the variance term that's dominating the test error, or the bias term that's dominating the test error. Right? Oftentimes that's what's happening. And so to see that in a more concrete setting, let's think about a one-dimensional regression problem, right? In this one-dimensional regression problem, this is the test distribution. So x is the dimensional, and y is the target, and this is the test distribution. Right? And what we're going to do is we're going to sample 7 points from this test distribution as our training set. Right? So imagine we collected a training set capital S of 7 points, then these are the blue points. And we're going to fit a linear model to these 7 points, right? And you get something that looks like this. The black line is the linear model fit to these 7 points. If I pick randomly another random 7 points from the test distribution, I fit a linear model to it. I train a linear model on this training set of 7 points. For these 7 points, I get this one. And I can repeat this process, right? So this is what I mean when I say, suppose we treated our training set as a random variable, and we, at least hypothetically, were able to repeat this process of collecting training sets of the same size, right? And you could certainly do this in simulation. What is the variability of our model class, given the training sets of this size, collected from this test distribution? We do the same thing for our more complicated model class, like quadratic, right? So I collected these 7, I get this quadratic curve. I get these 7, I get this one, so on and so forth. And you do the same thing for cubic. And then, I could, do this average, right? So now, if I do this process, I think I did this 1,000 times, right? The black line is the capital F of X, the average for those 1,000 models, given input X from this range. The green line is the variance, the average square distance between any particular model in that 1,000 models from the average model. And so and this is for linear, for quadratic, and for cubic. And so the bias variance decomposition states that the variance is simply the sum of the square distance between the blue line and the green line. And so as you vary the input x, you can actually measure the per input variance, which I have broken down here. The bias is what is the difference between the black line and the actual round trip label, right? So that's the vertical distance between the red dots and this black line. And that's this. Right? And the total test error is the sum of the two. Right? And you can do the same thought experiment for quadratic model classes and for cubic model classes. Right? And so, what does this mean? This means that if we had enough training data, this is not surprising by the way, if we had enough training in the cubic model, it's actually a really great fit for this data. Right? It has a very low bias. Right? If we had all the data in the world and we fit a really reliable cubic model, you would have very low bias, right? Because in the limit of infinite data, in the limit of infinite training data, variance goes to 0, right? For all model classes. Right? And so if the green lines were not there, then in the limit of infinite data, the cubic model class has the highest, has the lowest bias, which means that if we had enough data, there's no reason not to use the cubic model class. However, we only trained this very simple thought experiment on 7 training examples. And the cubic model, so the variance, the test error, is the sum of the bias and the variance, which is non-zero, because we don't have infinite data. And so it's actually very high for the cubic model class. On the flip side, for the linear model class, it's a very simple model class, not a lot of variability. So the variance is actually very small, but it has very high bias, right? It's not flexible enough to capture these nonlinear patterns in the data. So for a training data set of 7, it turns out, in this case, the quadratic model class is the one that actually has the lowest test error. It has the best trade-off between bias and variance. Any questions? So high variance, if your model class is high variance relative to the size of your training data, that implies overfitting. When you're overfitting to the idiosyncrasies of your for cubic, you're overfitting to the idiosyncrasies of a few examples here. Right? You randomly got a few examples over here, you have no examples over here. And for a cubic model class, this goes like crazy, right? So that's what high variance implies. Your model class is unstable with respect to training sets of this size. Right? If you were to randomly recollect another training set of a similar size, you might get a very, very different model. Right? Variance increases with model complexity. So cubic class is cubic has high variance than linear. And variance reduces with more training data. So the more data you collect, whatever model class you have, the lower the variance. In the limit of infinite training data, the variance goes to 0. If your model class is high bias, it implies underfit. Right? Even with no variance, your model class will have higher. Your model class simply cannot capture the complexity of the data, and therefore will have higher no matter how much training data you have. Bias decreases with model complexity, and it's independent of training set size. So now we get to the topic of model selection, right? Which is the idea of, okay, we have, in this case, let's say we have linear, quadratic, cubic, and we have data sets of this size, training data set of this size. Which model class should we use? Right? Finite training data, complex models overfit, some models underfit. How do we choose the model class with the best generalization? This is also, which means don't overfit too much. Right? Okay, generalize to the test set. The problem is that we can't measure the test error directly because we don't have it. We don't have the test data set. We can only sort of think about it in simulations or mathematics. In practice, in a real world 30 data set, 30 problem, we have our finite training set, and that's all we have. Right? We don't have access to the whole distribution. So the trick is to use a validation set. The idea is that in our original training data, right, that we've collected, the finite training data, we're going to split it. We're going to split it into a validation set, what's called a validation set, denoted by purple, and a new, smaller training set denoted by blue. And we're going to train models on the validation set, and we're going to evaluate the loss or the accuracy, or whatever loss we want, of those models only on the validation set, which we did not train on. So what does that mean? That means the validation set is somehow an unbiased sample from the test distribution, right? And we can use that to estimate test error. And it's important to keep training validation set. Because otherwise, so then if you overfit to this training set, right, then you can detect it because it gives much worse performance on the validation set. Can anyone tell me what's wrong with this set? Like, what's the limitation of this set? Yes? Correct. You are decreasing the amount of data used for training. And as we saw in the previous example with 7, you need more, or as we saw in the previous slide about overfitting versus underfitting and bias variance trade-off, the more data you have, the better, because you can then use more complicated model classes, right? So that's what's wrong with the setting. So another approach that's often more popular when estimating things like bias variance trade-off is called cross-validation. Right? And this particular example is 5-fold. In general, you do 10-fold, 20-fold, etc. Or leave one out. Well, how cross-validation works is as follows. You have your original training data. For 5-fold validation, we're going to split it into 5 equal partitions. Right? And then we're going to rotate by training on 4 partitions and evaluating on 1 partition. Right? So train on these 4, evaluate on this guy, train on these 4, evaluate on this one, and so on and so forth. This has 2 benefits. The first benefit is that, as you do 10-fold validation or 20-fold, with 5-fold validation, you're using 80% of your data as training, right? With 20-fold, you're using 95% of your data as training. And so you're using much more of your training data than otherwise than you did in the previous example where you just do a straight up training validation split. The second benefit is that it allows you to use all of your training data as test data. You've actually evaluated the performance of your model class on every original training data point, right? Which is something you could not do in the previous example. In the previous example, not only was your training data small, your validation data was also small, right? Because you're using only a small set of your original data as validation data. So now you can use all of your original data as validation data. So this is how you can use your data set, your one single data set to have some sort of an empirical estimate of things like overfitting, variance within model class, and things like that. Yes?
How do you consider your evaluated data unbiased if you train on
if you
it?
assume that the whole data set was sampled independently from the true distribution, and you do this partitioning uniformly at random, then the resulting validation data is also an unbiased sample from your true distribution. Therefore, it gives you an unbiased estimate of test error.
After you've trained on it already, and
But
then
you
use
never
it?
train on, right? So you only train on base 4.
Okay.
You would test on this. So you repeat this. So here you train 5 times. Here you train 5 times, right?
Okay.
So you never actually test
This
on
makes sense.
when you train model. Yes. Your question.
So how bad is it to use cross-validation error to actually select a model? So you have like 10 models, you
That's what you should
perform
do. So
cross-validation and then...
the standard practice is to use cross-borrow.
But will it overfit or will it...
It will okay. So it is standard practice to use cross-validation for model selection in many cases. You are still at risk of overfitting, right? It's less of a risk than it was before. I don't want to get into the details of that, but yes, because you are using the data twice, even though you're trying to keep it separate for separate purposes, you are using the data twice, so you are overfitting a little bit in this process. So you should be careful about that, and that'll become painfully apparent when you do the Kaggle competition. But it is standard practice.
So is there anything better?
In the case where you have gigantic data sets, then this is much less of an issue. You can actually just do this. And both data sets are big enough.
Okay.
You said that the first part is for validation set, yes, and we change it 5 times. So for example, in the first time we find the W and B, and after that when we change the validation set, we find another W. Now we have 5 W and B. Which one is the last one?
In practice, one common strategy, one popular strategy. So this is for model selection. What does model selection mean? Model selection means we want, in this particular case, model selection, you can use model selection for many different things. In this particular example, we're using model selection for picking between linear, quadratic, and cubic. Right? So we do cross-validation to say, okay, it turns out that we can estimate that the quadratic model class has the lowest test error based on cross-validation. So now we don't do cross-validation anymore. We train using the whole data set on the quadratic model class. But now that we've done this last step, we can no longer use that data set to estimate the error of the quadratic model class. But because we train on more data, we know the only thing that goes down is variance. So it's at least as good as what we estimate in expectation. Yes?
So is it something like we use cross-validation as like the first step before like touching the test set?
That's right. That's right, yes. So there is oftentimes people use a final test set, and this was something that you will encounter in the Kaggle competition, that is held out until the very end, until you've done everything, you've committed to a single model, and you will not backtrack. That's the final test set. And cross-validation is a step you use before final. You look at your final test set. That's a question.
If we increase number of partitions, should we expect the validation to be better?
Right, so in the limit, you can always do leave one out, right? Like if you have 1,000 training examples, you train on 999, you test on 1, and just rotate, right? And that's okay. The main reason why people don't do that is because of computational costs. Yes?
So once you pick a model, do you then use the same data to find the exact parameter values for that model?
Yes. So once you pick a function class, let's say linear, quadratic, or cubic, you use the whole data set. Typically, you don't have to do this way, but one common way to do this is to use the whole data set to train on, let's say, quadratic, and find the parameterizations of the quadratic model that has best performance on this training set. But then you can't use the data again to evaluate how well to estimate its test error, because you can't use it for both training and evaluation of test error. Okay, so let's just summarize. This is a complete pipeline. Training data, in this case, supervised learning, the label, we have a feature representation of inputs. We pick a model class, in this case linear, maybe multiple model classes like quadratic or cubic. We define a loss function. We do some sort of model selection. We have multiple model classes. and then we profit. Okay, so that's it. For next lecture, we will look at perceptual analysis aspect of sentence detail, and remember recipes for that.